In this video, we'll discuss very basic concept of control system. Those who have not gone through the control system part earlier don't have any concept on control system. This video will be useful for you. In this video, we'll start with very fundamental concept of control system. Particularly, we'll be discussing the open loop system, closed loop system, and how to find the time response of the control loop system. So we'll discuss here something about Laplace transform, that is more crucial things, important thing we'll introduce here. So please follow this one. So here in the control system, we'll deal with always one kind of system, right? So this is one basic concept. So every control system, the main element is your system. The system will accept one input and it will produce a corresponding output. So this input in control system form would write the reference input, it's in time domain R of t. So R stands for reference. So this is your reference input. Okay? And the output of this system, we'll call it controlled output, CT. So this CT is basically controlled output. So this R stands for reference and C stands for controlled output. So generally we want to get a controlled output from the system. So in signal system point of view, the system is defined by its impulse response. So if I call it impulse response is GT. Small g is the impulse response. So this is your impulse response. So if you understand signals and system, then it will be easy for you to understand. But here we will take different approach in control system. Okay. So what is the relation between CT, GT and RT? So this output CT is the convolution of the input signal RT. So this is the convolution sign and GT. Okay, we will not discuss convolution here. This is a part of signals and system. But here in control system, we will take different approach. We will work with in different domain, not in time domain. So we will work with in Laplace domain. So this is one important concept, the Laplace domain. Okay, Laplace domain. We wish to convert everything, all the time domain signals and systems in the Laplace domain. So what is the Laplace domain that you need to understand? Okay, if we have one signal in time domain xt, that will convert it to in Laplace domain, I'll call it LT, the Laplace transform. Then the small x, always this letter is used in time domain. So capital letter will be using to indicate Laplace domain. So small xt in the time domain signal or system impulse response, whatever it is, and that is converted to Laplace after taking Laplace transform, and here the variable will be small s, capital X of small s. This is the parameter. Okay, so this s can take one real value sigma, and it can have one complex part, imaginary part, this j omega. In general, it could be sigma plus j omega. This is the real part and this is the imaginary part. So that I will discuss later in detail, but here we will try to introduce the Laplace transform so that we can understand the system in a better way, in a simple manner. So we will This video will discuss everything in a very simple manner so that everybody can understand. Okay, so try to focus on this thing. Xt is your time domain signal, and if I take Laplace transform, we'll get capital X of S. Now what is the relation? The relation is very simple. So we can use this thing where the relation is that capital XS will get, just taking this thing, xt will multiply with e to the power minus this s, parameter s, and t, small t, time domain. Okay, then we will integrate with respect to time, and we will consider the entire time from 0 onward. We will consider that signal is present at 0 onward. So we will start from 0 minus rather, up to total time, positive side, infinity. So if you take entire time 0 to infinity, if you integrate, then you will be getting one result, and this one will be function of s. So capital X is a function of s. This is the parameter. Okay. So in this way, we will be getting the Laplace transform of time domain signal xt. So if RT is there here, this RT time domain signal, its corresponding Laplace will be, I write capital R of S. Right? Similarly, the Laplace transform of small ct will be capital C of S. Right? Similarly, this small gt, its Laplace transform, I write capital G of S. So we will transform everything, all the things. So small ct is replaced by capital C of S, small rt is replaced by capital R of S, and small gt is replaced by capital G of S in Laplace domain. So in Laplace domain, the relation is little bit different. What is the relation? The C of S is simply multiplied of this input R of S and this G of S. So this is the relation. This is simple multiplication. So this convolution is replaced by, this is the convolution in time domain. In Laplace domain, it is simple multiplications of input of R of S and G of S. Okay. So in other words, what you can write? So if you have one system, so what we will call it? This is a system. We'll write here. This G of S is the system, and its input, the reference input is R of S. So all in Laplace domain, and we'll get the controlled output, then write capital C of S. So here we can write that this G of S. What is G of S? Can I write? Because C of S is multiplication of RS and GS. So what is G of S? It is nothing but C of S upon R of S. Okay. So this G of S is called in control system as it is transfer function. This is basically a gain in Laplace domain. So output Laplace upon input Laplace. Okay, C of S upon R of S, this ratio is called transfer function. Here one condition obviously it should choose. There is no initial thing is there. Okay, so all initial conditions are made 0 in the system. Okay, so if you don't put any input, you should not get any output. That is the meaning. If it is that kind of system, then we can define transfer function. So transfer function is defined by C of S upon R of S, the Laplace transform of output, and Laplace transform input, this ratio is called transfer function. So you can see that this g of s is a function of s. So it can take this kind of thing, ratio kind of things. Okay. For example, I can take few example. So g of s could be like this. Suppose it is s minus plus 1 and this is s plus 2. It could be like this. Okay. So this ratio, suppose it is giving like this. So g of s can have some numerator and it can have some denominator. Okay. So in general, this transfer function can take here some part polynomial and denominator also you can have certain polynomials. In product form also we can write it down. Okay. So this product form, just see what I am saying this thing. This is s, I write this one is p1, this is s plus p2 and it can have more. Similarly, numerator I will call it s plus z1, s plus z2, this kind of factors we can get it. Okay. And these factors are having certain name. What are those things? So if you keep these factors or make these factors, so here numerator, no? So this numerator, if I consider, so what are the solutions? If I put it 0, numerator equals to 0. So s equals to minus z1 or s equals to minus z2. These are the solutions if I put numerator equals to 0. And these are called zeros of the system. This is called zeros of the system. So numerator if is becoming 0, if we make numerator equal to 0, that is called zeros. Okay. And zeros will denote as a circle form. We will discuss this thing in detailed way. And denominator if you make it 0, so next one is this thing, denominator if you make it 0, then this solutions s, so s plus p1 equals to 0, that means solution is s equals to minus p1 or s equals to minus p2. These are different solutions. So these solutions are called poles. So this name is poles. So zeros and poles, these are two important concepts, and poles will indicate using cross sign. Okay. So zeros will be indicated by circle and poles will indicate by cross sign. Now what is the basic concept of zeros and poles? Now you can see that whenever the denominator will become 0 for certain s value, so here s equals to minus p1, this value is becoming 0. So what is the gain? So g is basically is a gain, output by input. This is a transfer function, it is nothing but gain because it is output by input. So gain will become infinite if at s equals to minus p1. So at the pole position, gain is becoming infinite. So you will be getting a larger output signal. That's how it is called pole. Pole means vertical line. So almost very large signal you will be getting. And at zeros, s equals to minus z1, if I put, then this part will become 0. Everything gain will become 0. If gain is 0, output will become 0. Whatever input it is, doesn't matter. For any input, output will become 0. So that's how the output is 0. It is called zeros. So it will make output 0. Okay. So numerator equals to 0, that solutions will give you zeros. And denominator, if you make it 0, then that solutions will be calling as poles. So in this case, for this example, how many zeros and poles are there? So numerator is s plus 1. Okay. So what I will do for these zeros, I will put this numerator s plus p1 means s plus 1, that is equals to 0. If I solve, so what is solutions? S equals to minus 1. So position of 0 is at s equals to minus 1. And what is the pole? So here this is a polynomial s into s plus 2, that is equals to 0. So the denominator s into s plus 2, that part is 0. I will put it. So what are the solutions? We will get two solutions because second order, two factors are there. So the solutions are s equals to 0 for this one, and for this one s equals to minus 2, because s plus 2 equals to 0, s equals to minus 2. So we have two poles and one 0. So how to denote this thing in Laplace domain? Okay, so what I am saying that if Gs is given as s plus 1 upon s into s plus 2, we have seen that zeros we have got s equals to minus 1, and poles we have got at s equals to, this one is for 0 and another pole at minus 2. So two poles and one zeros. Okay, now how to represent this thing on s plane? I'll call it s plane. So we'll consider this one. So this is your real axis and this one is your imaginary axis, and I'll call it this s plane, Laplace plane, s domain plane. So this is the origin 0. Okay, now we'll put the zeros by, indicate by circle kind of things. Okay, so these zeros at s equals to minus 1. So this is a real axis. So this could be suppose minus 1. So here I will put it 1 0. So this position is suppose minus 1. This is at s equals to minus 1. Okay. Now what is the pole? Pole is s equal to 0. At origin you have one pole. So how to indicate this one? I'll indicate with these things. I have one pole at origin, s equals to 0, another pole at here, where it is at s equals to minus 2. At s equals to minus 2, I have one pole here and one more pole at origin, s equals to 0. And I have 1 0 only at s equals to minus 1. So it's not necessary that all the poles and zeros will be on the real axis. It could be on the s plane anywhere. Okay, so I'll take one more example about the system. Suppose if Gs is considered like this, so this is s square plus 3s plus 2, and this one is suppose SQ plus suppose 4 a square, right? And suppose this one, okay, I can make it 5 or 6, is that? It is 6. And this is suppose 9s. It could be. Okay, so in this case, so we can go for factorization. So what are the factors for this numerator? So this is s plus 1 If you go for that, and it will be s plus 2. I think it is very simple. And this one, if you can see, I can take s common, then it will be a square plus 6s plus 9. What is this? S plus 3, that square. Is it okay? Because square plus 2 into 3 is 6s plus 3 square is 9. That's how I have given in this way. So this is your g of s. So can you locate the poles and zeros? Yes, you can locate the poles and zeros in a very simple manner. Okay, so where is the poles and zeros? So this is your S plane. So where are the zeros? So numerator solution equal to 0. So S equals to minus 1. There is 1 0. Another 0 is equal to minus 2. And where are the poles? We have 3 poles because third order. It is 3 poles. So these solutions S equals to 0. And these solutions S plus 3 whole square equals to 0. So you have 2 solutions. Both are minus 3 and minus 3. Same solutions. So total 3 poles. Out of this, one solution is 0. Another one is at minus 3, minus 3. So we need to express all the things, right? So to include 0 at minus 1 and minus 2, you can see that I can put in this way. At minus 1, suppose here, and another one is minus 2. So this is your S equals to minus 1, and this is S equals to minus 2. We have 2 zeros. And how many poles? 3 poles. 1 pole at origin, and we will include this thing in this way. So here I'll put a cross sign because it is a pole at origin. And I have 2 more poles at minus 3. So this is your minus 3 point. So here I'll show 1 pole and 2 poles. So this way will indicate that 2 poles are there at the same place. It's a very, very near to this point, but we'll show these 2 poles in this way. Okay. So we have 2 multiple poles at S equals to minus 3. So still it is all the real axis, but we can have on imaginary axis or somewhere here. Okay. So let us take one more problem, one more example kind of things. G of S, if it is like this is a square plus 4, and if it is this kind of things, S into, not always that you need to get S only. Suppose I am considering A square times, this is A square plus this is suppose 2s plus, I can go for 5. Okay. So if it is a system, can you find poles and zeros? Then can you show the poles and zeros on S plane? This is important concept. Okay. So let us understand this thing. What are the zeros and poles? So numerator, if you make it 0, you will get zeros, and if you make denominator 0, you will get the poles. Okay. So zeros, what I will go for? This is square plus 4 equals to 0. So what is the solution? A square equals to minus 4, or as equals to square root of minus 4. Can you see? So square root of minus 1, we'll call it iota or I. So in this case, sometimes we'll replace by not I. So in contour system, we will go for this symbol J. Okay. So I is generally for index kind of thing or input kind of things. So in contour system, square root of -1, the symbol will use small j. So here, what I write? I can write it is square root of 4 times square root of -1, and square root of 4 is 2, and square root of -1, we'll call it j. So we'll get two components, plus and minus. So this is because square root of 4 is either +2 or -2. So we have two solutions. One is s equals to plus 2j, other one is minus 2j. Okay. Similarly, you can go for the poles. So what are the zeros? So zeros we are getting here. So s equals to, we are getting 2, 1. One is plus 2j, other one is minus 2j. Right? So this we can indicate first on the complex plane, S plane. This is real axis, this is imaginary axis. Okay, it is your S plane. So what to put? Plus 2j. It is on imaginary axis because the real part is absent. So I can write 0 plus 2j. So this is your j component. So I need to put this point at plus 2j here. This is equal to s equals to plus 2j. Similarly, I have one more 0 at minus 2j. So this could be here in below. This is at s equals to minus 2j. It is perfectly on imaginary axis because imaginary axis means j axis. Okay. Now, similarly, we can consider the poles. What are the poles? So we need to solve these equations. So if you solve this equation, what you will get? So I can go for the poles. For that one, so this one s square equals to 0 will give you s equals to 0 only. Okay. So first I am considering this thing only, s squared plus 2s plus 5, that is equals to 0. So this one, how can I write? S squared plus 2s plus 1. And this side I can put it, this 4, I can keep it on the right side, minus 4. No problem. Right? So this one, what I can write? S plus 1 whole square equals to minus 4. So as earlier, so square root of minus 4. So s plus 1 will be square root of minus 4. And square root of minus 4, you have seen that plus minus 2j. So what is this? S plus 1 equals to plus minus 2j. So what is this? S I can write, this 1 I can take in right side, it's a minus 1 plus minus 2j. Okay, so its real part is minus 1. Okay, the real part is minus 1 and imaginary term is plus 2j and minus 2j. So where you can put? We can put, so we will consider this one. It says minus 1. It's minus 1 and plus 2j. So here. So this is your minus 1 and minus 1 minus 2j, it could be here. So these are the two poles. So here this point is s equals to minus 1 plus 2j and this point is s equals to minus 1 minus 2j. So I have two poles, two cosine, we have shown it here on the complex plane, and two more at poles at origin. Okay, that also it should indicate. So this one, I have two poles here, 1 and 1 here. So we have total 4 poles. So two more poles at s equal to 0 and 0, and 2 more poles here, -1 plus 2j and -1 minus 2j. I think it is clear. So system can have some poles and some zeros. For standard system, for practical systems, number of poles will be more than or equals to number of zeros. So number of zeros cannot be more than number of poles. That is not the feasible system. Okay, that we'll discuss more later. Okay, so this is all about the system. Now, this kind of system, generally, whatever we will get it. So this is the system. I have said that this system is also called plant. Okay, in control system we can call it plant or system or controller, something like that. Okay, so this is a system and its gain transfer function we have denoted by h of s. It will take input, reference input rs, and it will produce controlled output cs. And if there is no feedback kind of thing, it is straightforward. It is called open loop system. This is called open loop system. And in open loop system, we have defined the transfer function Gs as the C of S upon R of S. This is your transfer function. So open loop gain or open loop transfer function. This is your transfer function or open loop gain. Okay. So sometimes what is happening, this open loop system is not stable. It may be unstable. So we need to understand what the meaning of stable and unstable system, that we will discuss later. For time being, just try to understand. If I apply some bounded input, so if I apply bounded input, if it is bounded input, bounded means this signal strength is not going towards infinity. Okay, signal strength is all time, it is finite. That is called bounded input. Okay, all time up to infinity, signal value is not going towards infinity. Input signal value. That's the kind of signal is called bounded input. And for all kind of bounded input, if I get always bounded output, okay, so you are applying bounded input, you are always getting bounded output, means output is not going towards infinity. Its magnitude is not increasing towards infinity. It is remaining finite. In that case, I will say that system is stable. In that case, the system will be stable. Otherwise, it will become unstable. If system output is going towards infinity, then system is called unstable. So system is stable or not, that is the major concern in control system. In control system, we will study this thing in detail, whether system is stable or not. If it is unstable, the question is how to make it stable. And then we need to understand how to check the stability. So that thing we will be discussing in lot. In control system, we will discuss lots of technique to study the stability of the system. So we will discuss those things one by one. We will discuss Routh-Hurwitz criteria. We will discuss Root-Lucas technique. We will discuss Nyquist plot. There are several things. Okay, all the topics we will be discussing one by one, and those are only for checking stability of the system, whether the system is stable or not. This is the main important concept of control system. So major part of the control system is checking just stability of the system. How to check system is stable or not. Okay, So that we'll discuss in detail later. So for time being, what I am saying that if system is unstable in this open loop form, we can make it stable if I take certain feedback kind of things. Okay, that is called closed loop system. We can provide negative feedback to the system. We can make the system stable. Right? So how to make it stable? So what is the closed loop system? Right. So far, if you are enjoying this video, can you please press the like button? Because it will help other can get the video and they can enjoy. So thanks for this. Now we'll move forward. So we'll try to understand what is the feedback control system. We have one open loop system. So the main system is this one. This is our system. And that system transfer function is G of S. Okay. What I will do, I will take one output on sample from this one, and I will fade it back to the input side. So this is the input side. So this input side here, the R of S will be applied in Laplace domain. Okay. So this output C of S is sampled. So this is C of S. So we are taking sample of this output. We are going to fade it back to the input side through another system. So this is called feedback network. And this feedback network, it has also certain transfer function. And that transfer function, I will call it H of S. So H of S is the feedback network. So this is your feedback network. Okay. So this is fed back to this side. So this is coming here. So this side CS is coming here. This is the input to this feedback network, and it will produce certain things here. And that thing will be compared here. We will compare with this RS. Compared means this is positive, and if it is negative, then it is called negative feedback. If I compare in this way, then whatever things we will get it, that is called negative feedback. Because this strength is going to reduce. Whatever thing is coming here, that is, you reduce certain things, then certain actuating error, I'll call it E of S, will get here. Okay. So remember, if this is negative, then it is negative feedback. But if I add it, if I add these things, whatever things we are getting here, if I going to add, this is plus sign again, then that is called positive feedback. Okay. So we can have two kind of feedback. One is positive feedback as well as negative feedback. But commonly we'll use negative feedback because this negative feedback will make the system more stable. So stability improves if we use negative feedback. Okay. So that's how in control system generally we will be using negative feedback. But we can use positive feedback sometimes. So if you use positive feedback, gain is increased, but system may become more unstable. There is a tendency that system will become unstable. Okay. So if you wish to improve the stability, you need to use negative feedback. But even though you are using negative feedback, there is no guarantee that system will become stable. You need to check it again. There is no guarantee. But it can make the system more stable. So in open loop system, G of S was unstable. Using closed loop, we can become the system, overall system may become stable. Okay. So how to find the overall system gain? Can I find overall system? This is not very tough. So how to find it out? So can you check these things? So this is your G of S. Okay, this is your H of S. So this, whatever is coming, it is C of S. So C of S is the input. So what is the output? So output is always the multiplication of input and gain. So this output is CS into HS. So this CS into HS is compared with RS. So what is ES? Can I write E of S? Yes, we can write E of S. This actuating error, this error will be this RS minus these things. Okay, so this is your RS minus this part. This part is CS times HS. Now what is the corresponding output? Now if I consider this system, main system, this is our main system or plant. Okay, so output CS, I will take different color. So CS is nothing but the product of ES into GS, because ES is the exact input to system and GS is your transfer function of the system. Now if I replace ES by this one, what is the ES? It is the RS minus CS times H of S. This is multiplied with G of S. So now if we expand it, this is R of S into GS minus G of S. This is the product of these three, H of S and C of S. These three terms product. Now I can take this one to left side. So if I combine these things, so what I will get? I'll get this one. So can you see? This is your CS and this part is coming here, plus sign, this minus, if it is coming to left side, it will become plus GS HS into CS, and that will give you RS into GS. So from here, this CS and this CS we can take common. Okay, then RS we can divide, and this factor we can take right side. So can you see this thing, this CS upon RS, because this is your transfer function of the system. Exact input is RS, exact output is CS. So output by input is called transfer function, and that we can find out. So what is the value? So you will be getting GS in numerator, and denominator, this is 1 plus this is GS and HS. Can you see? Can you simplify it? It's very easy. So this is called closed loop transfer function. This is called closed loop transfer function. Or closed loop gain. So closed loop transfer function will be the open loop transfer function GS upon 1 plus GS times HS. So we can simplify. What the meaning is that we can simplify this one. So we have one system GS and we have one feedback HS, and we can compare here. Okay, this thing is coming and this one, and we are getting feedback here, and then this thing will be comparing here. Okay, so this is positive and this is negative. This gain, system gain is GS, open loop system gain, and closed loop, this feedback network transfer function is H of S. Input is R of S, and controlled output is C of S. And we have seen that this total thing, C of, so what we want, we can simplify this one to one system, no, that will take this kind of, it is a one system which will produce the same result. This is your R of S, and it will give you C of S, and we will call it transfer function T of S, suppose. Okay. So what is T of S? So T of S, so actually this block, this entire block we can reduce to a single block T of S. We can reduce by T of S, where T of S is given by, what is the value? This thing, G of S upon 1 plus G of S times H of S. So you can see that poles and zeros of open loop system is completely modified. Okay, so closed loop gain T of S will have different kind of zeros and poles compared to the open loop poles and zeros. So if I put it this GS equals to 0, from here we will get zeros, and if I consider 1 plus GS, this polynomial, if I make it 0, then if I solve it, then we will be getting poles. But these are called closed loop poles. Okay, these are called closed loop poles. And stability depends on poles. So this is one single statement now I am making. The stability depends on only poles, not on zeros. Okay, and how to decide this thing, that we will be discussing in the next class, not in this way. Okay, so next class we will be discussing in more detailed way. We will introduce transfer function. Just we have mentioned this thing, what is transfer functions and what is the Laplace transform, but we will discuss more about Laplace transform. So if I want to discuss the Laplace transform in this video, it will become too lengthy. So in the next video, we will discuss Laplace transform, and we will see that how to find the response of the system using Laplace transform. Very quickly we can get it. So we need to understand Laplace transform well. And I will tell you that contour system is not a difficult subject. It's very easy subject. If you follow my lectures, you will be getting everything. All the concept you will be getting. I will be discussing all the concept very neatly. Just follow my videos, you will get it. Don't skip any part. Try to understand everything. Okay? And you will see at the end that you will be able to solve all the problems. And frequently problems are coming in all the exams, including GATE exam. In a semester also you will be getting lots of problems. Only problems. From different chapters you will be getting the problems. Okay, and I will discuss lots of problems in my channel. Don't worry, you will get everything. Okay, so I will stop it here today. So we will continue this thing, and if you have not subscribed the channel, if you are enjoying this thing, you may subscribe this thing if you wish to get more videos in this channel. And if you have not given the like button, so if you have enjoyed, you can press the like button. Thanks for this. So we will continue. Okay. Thank you. Thank you very much.